Hello and welcome back to Math Class in Session, continuing with our unit on curve sketching, critical points, and local extrema. A critical number, c, is a number in the domain of a function where the derivative is either 0 or the derivative is not defined. Critical points, c, f of c, usually correspond to local extrema. If the derivative is undefined at a critical point, then there is a vertical tangent or a cusp in the graph at that x value. That would be an interesting point because it would be in the domain of the actual function, but outside the domain of the derivative. First derivative test. Well, it's not really a test, it's a way to discern when we found a critical point whether it's a local maximum or a local minimum. If the derivative changes from positive to negative across a critical number, then there is a local maximum at the critical number. And it would look like this on a prime line, changing from positive to negative as we proceed from left to right. And it only stands to reason because if we're climbing, and then descending, we must have reached a local maximum. So the first derivative test really is common sense. If the derivative changes from negative to positive across a critical number, then we must have reached a local minimum. And it would look like this on the prime line, descending to a point and then increasing. So we must have come down and then gone back up, so that's a local minimum. Again, common sense. If the sign of the derivative does not change across a critical number, then there's neither a max nor a min at that critical number. And it could look like this if they were both positive. Example, analyze a function for local extrema and sketch. Solution, draw a prime line. Differentiating, y prime of x equals 3x squared. Drawing our prime line and putting the critical number on it. Now 3x squared equals 0 implies that x must equal 0. And evaluating the intervals as we're used to doing by now. On the left, anything squared goes positive, and on the right, anything squared, of course, still goes positive. So this is an example of increasing to a point, and then continuing to increase. So there's going to be a horizontal tangent when x equals 0, and the graph will be always increasing. A sketch of it will look like this. The cubic that's been shifted up 5 units. Let's do another one. Analyze a function, another cubic for local extrema and sketch. Solution, draw a prime line, which means differentiate. Set the derivative equal to 0, and I divided through by 3. Solve to find the critical points. Well, it's a quadratic, so I solve by factoring. And x equals -3 or -1. Those will be entries on our prime line, -3 and -1. Analyzing the intervals to the left of -3, subbing into the derivative. Well, subbing in something large and negative will square and become positive. Subbing in between -3 and -1, let's sub in -2 to the derivative. -2 squared is 4 times 3 is 12. -2 times 12 is -24. Combine those, you got -12 plus 9. That's going to be negative. And then substituting in something large to the derivative, when squared, will become huge and positive. So there we have our prime line. And we can examine this and see that we're increasing to a critical point at -3 and then decreasing. So this must be a maximum. There must be a maximum at -3. A local maximum when x equals -3. Where did the 2 come from? Well, be sure that you don't sub -3 into the derivative. No. Points come from the original function. So subbing in -3 to the original gives us a y value of 2. Looking at this again, we have a descending function to an x value of -1 and then increasing. So that must be a local minimum. There's a local minimum when x equals -1, and we get the y value by plugging into the original function again. Putting these on our grid, we have -3, 2, and we have -1, -2. And looking at our cubic, this number on the end of a polynomial, the constant term on the end of a polynomial, is always the y-intercept. So we could put that on our graph here as well. And so we know that this is a local maximum, so we'll come up to and then descend from our local maximum, and then descend to and then come up from our local minimum, up through our y-intercept, and on up. Label the graph, and this is sketching a cubic using max and min. Let's do it again, this time with a quartic. Analyze the function for local extrema and sketch. Solution method, draw a prime line, a very useful activity. Drawing a prime line will involve differentiating 4x cubed minus 12x squared minus 16x, setting it equal to 0, and I common factored out 4x out of my derivative, leaving a factor which is itself a quadratic and can be factored. And we have critical numbers, 0, 4, and -1. Put them on a prime line, 4, 0, and -1 in the right order, and evaluate the intervals. Well, to the left of -1, we have the arrow here, so we can sub in something very large and negative. Large and negative. Well, large and negative when cubed is negative. And so this whole section will be negative, sloping down. Between -1 and 0, we have to sub in something to our derivative here. How about to the factored version? -1/2. Well, if I put -1/2 in here, I've got a negative factor. Put -1/2 in here, I've got a negative factor. Put a -1/2 in here, I've got a positive factor. And so it will be a negative times a negative times a positive, and that's a positive. Plugging in 1 to our factored derivative, it'll be 4 times 1, which is a positive, times a negative times a positive. So we have a positive times a negative times a positive, and that's a negative for this section of the derivative number line. And then something large and positive into, we could go to this version, something large and positive, the cubic term takes over, and we have a positive. This said, this gives us information that at an x value of -1, we have a minimum because it's descending and then increasing. So a local minimum when x equals -1. And where do we get y? From the original function. And then it's increasing until x equals 0 and then decreasing. So there's a local max when x equals 0. And where do we get y again? Plug in 0 to the original, and y is -1. And then decreasing to an x value of 4. So there will be a minimum when x equals 4. And where do we get the y value to go with 4? Plug 4 in here. Do the math yourself. Pause the video if necessary, and you'll find out that the y value turns out to be -129. Placing these on our grid, -1, -4 looks like about there. 0, -1 is about there. And 4, -129 is right around there. I made the scale count by 25s here to make room for this -129. And we know that we are going to descend to this minimum and then increase. So it will come down to this minimum and then increase. It increases to 0, so it increases until x equals 0, and then it decreases. So it comes down, then it increases, and then it comes down again. And then it turns around and goes back up because it says increasing after x equals 4. Joining them together, labeling the graph. Moving on, let's go again. Analyze the function for local extrema in Sketch. Solution, draw a prime line. Well, I've rewritten the function because it's 3 times x minus 2 to the exponent 1/3. And now differentiating, it will be x minus 2 to the negative 2/3, which implies that that's actually in the denominator squared under a third root sign. We know from our fractional or rational exponents. And we have a critical number when x equals 2. So we can make our derivative number line and put 2 on it. And to the left of 2, well, plugging in to the derivative a number to the left of 2, whatever it is, when you square it, it's going to turn positive. Same with on the right. Now the interesting thing about this particular function is that there's a point here. There's a critical point when x equals 2. The critical point at x equals 2, 2, 0. Because when you plug in 2 to the original, you get 2 minus 2 is 0, and third root 0 is 0, so 3 times 0 is 0. This is interesting because 2 is a part of the domain of the original, but 2 is outside the domain of the derivative. You can't plug 2 in here. It's a restriction. 2 minus 2 is 0. So 2 is part of the original domain, but not part of the domain of the derivative. And from our note, if the derivative is undefined at a critical point, then there is either a vertical tangent or a cusp in the graph at that x value. I wonder which it is. Let's look. Consider the following. The graph of y equals x cubed I've shown here. It's the blue line. And the graph of y equals x I've also shown. The black line is y equals x. If we were to take the inverse of y equals x cubed, which means y becomes x becomes y, take cube root both sides, we have y equals third root x, the inverse of y equals x cubed, which is the reflection across the line y equals x. Y equals third root x must look like that. So if we use y equals third root x as the parent function of y equals 3 third root x minus 2, and realize we'll take this graph, vertically stretch it times 3 and shift it to the right 2, we've made our sketch. And here it is on the zoom out. Let's do another example. Analyze the function y equals x plus 3 to the 2/3 for local extrema in Sketch. Solution, draw a prime line. That means we have to differentiate, so 2/3 x plus 3 to the negative 1/3, which puts it on the bottom under a third root sign. And we have a critical number here at negative 3. Why? Because at negative 3 the derivative is undefined. So on the prime line goes our critical number x equals negative 3. Analyzing to the left, well, let's plug in something large and negative. Taking the third root of something negative is a negative. Let's plug in something large and positive. Taking the third root of something positive is, of course, a positive. And we do have a critical point at negative 3. Negative 3, 0 is a critical point. And we can see that that must be a minimum because we descend to it and then increase. So we have a minimum at negative 3. Negative 3, 0. But what does our graph look like? We recall the note. If the derivative is undefined, which it is at this critical point, negative 3, 0, then there is either a vertical tangent or a cusp in the graph at that x value. And we note that x plus 3 to the 2/3 is actually third root of x plus 3 squared. And the third root of x plus 3, we know from the previous example, looks like this, because it's a third root function shifted to the left 3. So if we could take all the y values of this third root function and square them, we'd have the third root of x plus 3 squared. So we have to square all the y values. And when you square these negative y values, they turn positive. So they'll be up here somewhere. And when you square these y values, they'll be positive as well, and perhaps a little higher. And there we have it. Y equals x plus 3 to the 2/3.